I want you to picture something for a second.
Yeah.
Picture that heavy, incredibly loud vehicle that stops at the end of your street, every single week. You definitely know the one.
Oh, yeah. It looks like just a giant, simple steel box on wheels.
You're right.
Right. Just rumbling through the neighborhood.
Exactly. But what if I told you that the engineering hiding inside that seemingly basic box is actually more sophisticated and deals with way more complex physics than factory machinery costing 10 times as much?
It really is the ultimate illusion of everyday life. I mean, we see this massive vehicle swallow our bins, and we just walk past it without a second thought.
We barely even look at it.
Right. We're completely unaware of the mechanical warfare happening right behind that steel wall.
And that's what we're getting into today. We're pulling from a brilliant technical breakdown for this deep dive. It's an engineering article by a writer named Mayton, and he dives really deep into the fluid dynamics and mechanics of these machines.
Yeah, his analysis is fascinating.
Our mission today is to essentially peel back the curtain on this invisible machinery. We're going to look at exactly how these rolling hydraulic beasts manage to solve what turns out to be, one of the most mechanically difficult tasks on the planet.
It absolutely is.
So after today, the next time that truck delays your morning commute, you aren't going to look at it as just a garbage truck. You're going to see it for what it really is, a high-stakes mobile physics laboratory.
I love that. Framing it as a laboratory is so fitting because to truly appreciate the machine, you have to understand the specific enemy it's fighting.
And the enemy is the cargo itself, right?
Exactly. Think about it. If you design a machine for a modern manufacturing factory, you know the exact parameters of the material it's going to handle.
Right. It's predictable.
Yeah, the density, the temperature, the shape, the tensile strength, everything is a known variable.
The machine on the factory floor is basically dealing with a controlled universe. But household and commercial waste, that has to be the most mechanically inconsistent material on Earth.
Without a doubt. A refuse collection vehicle receives a completely chaotic mix. It gets rigid metal objects right next to soft food waste.
Just totally random stuff.
Yeah, extremely dense materials mixed with hollow plastic bottles, items that compress perfectly, and items that absolutely refuse to yield.
Not to mention all the liquids.
Oh, the liquids are a nightmare, unpredictable draining, plus sharp objects like glass or jagged metal that actively threaten the machine's internal seals and hydraulic lines. The machine has literally no idea what's coming next.
And there's no sorting or pre-processing on the truck. It just has to deal with it. Which brings us to the core mathematical problem that basically dictates why these trucks are engineered the way they are.
Right, the volume issue.
Yeah. A standard rear-loading truck body has a volume of about 20 to 25 cubic meters. But loose, uncompacted waste is surprisingly light for its volume. It has a bulk density of roughly 100 to 150 kilograms per cubic meter.
So if you do the math on that, dumping the trash in without altering it means that 20 cubic meter box would only hold about 2,000 to 3,000 kilograms of waste.
Which is roughly 3 tons.
Exactly. And for a heavy-duty commercial vehicle of that massive footprint, 3 tons is just a laughably tiny payload. The truck could fill up by volume almost immediately.
It would have to make dozens of trips back and forth to the disposal facility every single day.
Yeah, you'd have fleets of thousands of trucks constantly driving back and forth, burning fuel, clogging the roads, and they'd just be hauling mostly empty air.
That would instantly bankrupt the entire urban waste management system.
It would. The very existence of a functional, economically viable modern city is entirely reliant on solving this specific volume problem, and the solution is the compaction ratio.
Because these machines don't just carry waste, they actually structurally transform it.
Absolutely. A modern truck achieves a compaction ratio of 4-to-1 up to 6-to-1.
That is an absurd physical transformation. You are essentially turning a mountain of loose trash into solid concrete while you're driving down the street.
It shrinks the volume by up to 80%, so it turns a useless 3-ton payload into a massive 12 to 18-ton haul.
Try to picture this. It feels like the absolute nightmare of packing a suitcase. But it's a suitcase where someone is randomly tossing in bowling balls, wet towels, broken glass, maybe some empty cardboard boxes.
That's a great way to visualize it.
And your job is to automatically zip that suitcase shut and magically shrink it down to a fifth of its size, all without ever looking inside to see what you are squishing.
Achieving that 6-to-1 ratio on such chaotic material requires just an unbelievable amount of highly choreographed physical force, which, I guess, brings us to the heart of the beast.
The hopper and the packer blade.
Yes. It starts at the back in the hopper. This open loading area is essentially a buffer zone. It holds the contents of the incoming bins while the internal machinery finishes its previous cycle.
I always just assumed the blade itself was a giant metal wall that pushed the trash straight to the back, like a larger version of one of those under-the-counter kitchen trash compactors.
Just a simple linear push to shove everything out of the way.
Yeah, exactly. Just push it back and be done with it.
Well, engineers learned early on that a linear push is actually the worst possible way to handle this material. If you use a flat wall on this kind of chaotic, tangled waste, you don't compact it cleanly at all.
What happens instead?
You just smear it around. And worse, because garbage is full of springy interlocking items like plastics and wire, when the flat wall pulls back, the sticky, tangled waste gets dragged right back out into the hopper with it.
Oh, wow. So the trash acts like a giant, disgusting spring.
That's exactly it. So the Packer blade avoids this by following a highly engineered three-part geometric path. First, it sweeps downward and forward.
Down and forward, okay.
Yeah, this downward motion acts like a giant set of jaws. It shatters and breaks up large, rigid items like furniture or thick cardboard boxes, forcing them down toward the opening.
So it basically has to chew the food first, breaking the structural integrity of all those big items.
Precisely.
Oh.
Then comes the second phase. It pushes violently rearward, compressing that freshly chewed material against the immense wall of garbage already packed into the truck.
And the third phase.
Finally, it sweeps upward. This upward sweep clears the opening of the body. It literally shears off the face of the waste plug. That way, when the blade returns to its starting position, it leaves a clean face.
Oh, so it doesn't drag the trash back out.
Right. It's a very precise scoop and pack motion.
I mean, the force behind that scoop must be massive if it's shattering furniture. The source analysis points out that the hydraulics powering this blade operate at a staggering 200 to 300 bar of pressure.
Yeah, the numbers are huge.
To put that in perspective for you listening, a standard car tire is inflated to around 2 or 3 bar. This hydraulic system is running at 100 times that pressure.
And that translates to about 20 to 30 tons of physical force at the point of contact, right where that blade meets the waste. It's just a staggering amount of power.
It really is.
Crucially, though, the hydraulic cylinders driving this are double acting.
Wait, double acting. So they aren't just pushing forward under pressure and letting massive springs pull them back.
No springs here. They apply controlled, high-pressure fluid force in both directions.
Oh, I see. Why is that necessary?
Because if the blade jams on something during the compression stroke, and honestly, dealing with trash, it inevitably will, it needs enough raw power to safely pull itself backward, clear the jam, and reset.
Oh, that makes sense. Gravity or springs would never be able to dislodge a blade wedged into 15 tons of compressed metal and plastic?
Exactly. You need a hydraulic power to pull it out just as much as you need it to push it in.
Okay, so we have a machine generating 30 tons of dynamic force, swinging a steel blade hundreds of times a day, trying to crush bowling balls and wet towels into a dense brick.
Right.
Now, this solves the volume problem perfectly, but it seems like it creates a massive structural problem. The metal box holding all this highly pressurized, expansive material should, logically, just burst apart at the seams.
You'd think so. The sheer scale of the structural engineering required to prevent exactly that is fascinating. The body of the truck is essentially an armored pressure vessel.
It has to be, with all that force.
Yeah, it has to withstand the static weight of 15 tons of trash. Sure. But more importantly, it has to handle the dynamic impulse loads.
The impulse loads from the blade slamming into it.
Exactly. Every time that Packer blade slams 30 tons of force into the load, a shock wave of pressure transfers directly into the floor, the sidewalls, and the rear frame of the truck.
Hundreds of times a day.
Every day, for years.
That's incredible. But beyond the physical stress, there is a chemical warfare aspect to this too. Because when you compress that much biological and commercial waste, you squeeze out all the liquids, creating something called leachate.
Ah, yes, leachate. It is a highly corrosive, toxic sludge.
Sounds lovely.
It's terrible stuff. It's a blend of biological waste, chemical residues from cleaning products, battery acids, decomposing organic matter. It's a nightmare concoction.
And if you put that in an unprotected steel box,
The metal would literally rust from the inside out in a matter of months. So the inside of the truck must be lined with specialized internal coatings, complex drainage systems, and specific corrosion-resistant steel alloys.
just to survive the daily chemical bath.
Right. It is essentially a mobile chemical containment vessel on top of everything else.
Okay, so it can crush the waste, contain the pressure, and survive the acid. But the ultimate test of all this armor and hydraulic power has to be the end of the route, the ejection system.
Yes, getting it out.
It's one thing to shove all this stuff in and pack it tight, but getting it back out seems like a completely different nightmare. You've manufactured a 15-ton, highly cohesive, practically solid brick of garbage.
A very stubborn brick.
Right. You can't just tilt the truck like a dump truck and expect a perfectly fitted sticky brick to slide out.
No, definitely not. The friction against the walls and the floor is just immense. The garbage has been pressed into every tiny microscopic groove and corner of the truck body.
So how does it get it out?
To get it out, a full-width ejector blade has to travel the entire length of the truck, from the front cab all the way to the back tailgate, physically shoving the solid 15-ton mass.
Pushing a mass like that reminds me of trying to force a huge, sticky block of semi-dry cement out of a giant tube. The resistance must be unbelievable at the very beginning.
Your cement analogy hits on the exact mechanical challenge here. Overcoming static friction. The ejection process is actually the single highest peak hydraulic demand of the truck's entire day.
Really? It's
Yeah.
more than the crushing.
Yeah. The system has to generate an immense initial surge of power just to break the brick loose from the walls, but once the mass starts sliding, it shifts from static friction to dynamic friction, which suddenly requires less force.
Wait, if the hydraulic system keeps pumping at maximum pressure after the brick breaks loose, wouldn't the blade violently accelerate and shove the whole mass out too fast?
It would. That would violently shake the vehicle, potentially tipping the truck or blowing out the hydraulic seals entirely.
So how does it not do that?
The flow rates and the pressure relief valves must perfectly tune themselves in real time. They deliver a massive spike in pressure to break the static friction and then instantly regulate the flow to maintain a constant, smooth push.
Wow, so it keeps the mass sliding steadily without stalling or jerking.
Exactly. It's a very delicate, fluid dynamic operation.
The fact that a truck manages that complex operation at a disposal facility is impressive on its own. But this extreme, heavy industrial factory work is happening while the machine is actively navigating fragile, real-world urban environments.
Which brings us to the high-stakes balancing act. This is where fluid power directly intersects with urban logistics, because we've just pushed 15 tons of solid mass toward the front of the truck as it fills up.
And the consequence of that is a drastic shift in weight distribution,
Exactly.
because a refuse collection vehicle begins its route completely empty and ends it fully loaded. But as the trash is packed in from the back, that giant ejector blade is slowly pushed forward toward the cab to make room.
Right, the mass is moving.
This means the truck physically handles differently, like braking, turning, accelerating at the end of the route compared to the beginning, doesn't it?
It does. The center of gravity is constantly migrating forward as the mass builds up. And this is not just a matter of the driver pressing the brake pedal a little harder. It's a strict legal and operational constraint.
Because of the weight limits.
Yes. Cities have a rigid axle weight limits to prevent heavy trucks from destroying municipal infrastructure, like bridges and asphalt.
You know, I would have assumed the danger of shifting weight was the truck tipping backward on a steep hill or something.
Well, while stability is certainly a factor, the more immediate daily threat is destroying the roads. You can easily hit the maximum legal weight limit on the front steering axle, while the back of the truck is still volumetrically empty.
Oh, wow.
Yeah, if the center of gravity shifts too much and maxes out that front axle prematurely, it's a massive operational failure.
Yeah.
The driver has to stop the route and go empty the truck.
So they have to plan around that.
Entire routes are mathematically planned around this shifting center of gravity. They have to predict exactly how the load will distribute itself at every stage of the morning.
So the routing software is effectively performing real-time physics calculations for every cul-de-sac.
That's wild.
And speaking of the physical toll on the vehicle, the weight distribution severely impacts the tires. The source material specifically calls out, quote, tire torture.
Oh, tire torture is the perfect term for it. These tires operate under conditions that highway trucks never experience.
How so?
Well, the constant stop-start maneuvering at low speeds prevents the tires from properly cooling down. This repeated flexing of the rubber generates brutal heat deep inside the tire carcass.
Plus, they're dealing with the shifting load.
Exactly. Add the shifting, asymmetrical loads we just talked about, plus scraping against concrete curbs, hitting potholes, and rolling over the sharp glass and metal that inevitably falls out of the bins.
It's a miracle they don't pop constantly.
Managing tire inflation and thermal wear is actually a critical safety issue. I mean, a blowout on a tire bearing the asymmetrical load of a 15-ton shifting brick in a residential neighborhood would be a total disaster.
And while the truck is fighting the ground beneath it, it also has to reach out and interact with the unpredictable environment beside it. Let's talk about the automated lifter arm.
Ah, the lifter. Yes.
You sit in your living room, you hear the truck stop, and you hear the mechanical hum. That system has exactly 5 to 10 seconds to reach out, grasp a bin, invert it completely over the hopper, shake it to ensure the wet material falls out, and return it upright.
And think about the mechanical variables that ARM encounters on a daily basis. A standard 240-liter domestic bin might weigh 80 kilograms.
Right.
But then the truck turns the corner, and the exact same hardware has to lift a 1,100-liter commercial dumpster that weighs 400 kilograms.
I always figured the driver had to flip a switch to change the hydraulic pressure settings depending on the size of the bin.
The advanced systems do use sensor feedback, sure, but the core mechanics still rely on a brilliant balance of brute force and delicate precision.
Delicate precision from a garbage truck.
Yeah. The lifting arm has to be sensitive enough not to crush a brittle plastic bin in the middle of winter, but at the same time, it has to be powerful enough to rip a massive commercial dumpster off the ice if it's physically frozen to the ground.
And do all that without spilling the contents onto the street.
Exactly. It's an engineering marvel.
But what happens when the precision fails or the system encounters something it literally cannot crush? Let's say a worker accidentally tosses a solid concrete block or maybe a thick steel gas cylinder into the hopper and the packer blade comes down on it.
This is where the immense power of the hydraulic system actually becomes its own worst enemy.
Oh, really?
Yeah.
Yeah.
If the packer blade hits an uncrushable object, it stalls. But the hydraulic pump doesn't know the blade is stuck. It just keeps trying to push.
It just blindly pushes against the block.
Right. The system will quickly reach its absolute maximum pressure, that 300 bar limit we discussed, and hold it there, locked in a total stalemate with the concrete block.
So the pump is just endlessly slamming fluid against a wall. That
Ow.
can't be good for it.
It's terrible for it. Forcing hydraulic oil over a pressure relief valve at maximum capacity generates immense shear friction. This literally boils the fluid.
Wait, it boiled the hydraulic oil.
Yes. The intense heat destroys the molecular chains of the oil, drastically degrading its lubricating properties, and quickly melts the internal rubber seals.
Wow.
So until a human operator intervenes to reverse the blade, the machine is actively destroying itself from the inside out, just trying to complete its programming.
That is intense. Now, generating that kind of raw, destructive power requires a massive energy source. Historically, the source notes that these trucks used a powered takeoff, or PTO, connected directly to the truck's main driving engine to run the hydraulic pumps.
Yeah, a PTO is essentially a mechanical shaft linked to the engine's transmission. So to generate the hydraulic flow needed to, say, crush a mattress, the driver had to rev the massive primary diesel engine to high RPMs while the truck was sitting perfectly still.
Revving a heavy-duty diesel engine at 5 a.m. in a quiet residential neighborhood just to crush some cardboard boxes. Sounds like a total nightmare for noise regulations.
Oh, it absolutely is. Which is why noise ordinances have forced a massive shift in how these systems are engineered today. Modern trucks are moving away from those PTO systems toward independent electric or battery body drives.
So the massive diesel engine can just drop to a quiet idle or shut off completely, while a separate, nearly silent electric motor spins up to generate the 300-bar hydraulic pressure.
Exactly. That shift is a direct engineering response to community relations and legal limits.
That makes a lot of sense.
However, it introduces a new frontier of energy management. The onboard battery system must be perfectly managed so it doesn't completely drain.
Especially when the truck suddenly needs that massive, sustained spike of power for the ejector blade at the end of the route.
Right, you don't want to run out of battery right when you need to push out 15 tons of solid garbage.
Bringing this all together, we started by looking at a loud, smelly, slow-moving steel box on the street. But Metten's engineering analysis completely strips away that illusion.
It really does. These machines operate at a brilliant, necessary intersection of structural engineering, extreme fluid power, dynamic vehicle physics, and strict urban logistics.
It's incredible when you break it down.
There is not a single redundant part on them. They are not over-engineered at all. Every ounce of complexity, from the geometric path of the blade to the thermal management of the hydraulic fluid, is an absolute requirement to solve the practically impossible task of handling chaotic waste.
So true. The next time that truck stops at your curb and takes 7 seconds to empty your bin, you will know.
Yeah.
You are witnessing a precision hydraulic marvel hiding in plain sight. It is a mobile factory doing the impossible perfectly every single day. But before we let you go, the source material leaves us with one final, truly provocative puzzle. We just spent this entire deep dive exploring the Herculean effort, the 30 tons of force, and the 300 bar of pressure required to compress this chaotic material into a dense 15-ton rock-solid brick.
We did.
But what happens on the receiving end? Imagine the jaw-dropping scale of the machinery and the structural engineering required at a transfer station just to break that massive, cohesive, 6 times density brick back apart so it can actually be sorted or incinerated.
That is a whole different level of engineering.
It really is.
Yeah.
Something for you to think about the next time you take out the trash.